Hello everybody, my name is Mr. Costanza. This is Regents Science Live. We're going to prepare you for the chemistry Regents tomorrow. Tomorrow it's in the afternoon from 12 to 3. And this is the first time we've had this in 3 years, so it's nice to be back. And to my right, I have two students that are going to help me. I've got Stevie and Carson. They're going to answer the Twitter feed and the phone number. So please call, please tweet any questions you have tonight, and I'll be happy to answer them for you. Now, before we get into some questions, I just want to give you an overview of the tests and a few hints that will help. So I'll use the Elmo here to do that. So as we know, the test is tomorrow in the afternoon. And when you take the exam, make sure you have the proper utensils. Writing utensils. You need blue or black pens. You need to use that for the bubble sheet. You also need pencils in case there's a drawing involved, but really pen is the best thing to use for the exam. And also a non-graphing calculator. You cannot use graphing for this exam. The test breakdown, there are actually 4 parts to it. There's part A, which is 30 multiple choice. Part B1, which is an additional 20 multiple choice. And then you have 2 what are known as free response questions, part B2 and then C. 15 for B2 and 20 for C. As far as grades are concerned, if you're looking to get 100%, you have to get a perfect score. Nothing rounds up to 100. 85 out of 85 questions. If you're looking to get above a 90, you'd have to get at least an 80 out of 85 to be safe. To get an 85 or higher, you'd have to get 75 out of 85 to be safe. 75% or higher, you'd have to get 65 out of 85 to be safe. And then, if you just want to pass the course or pass the exam with a 65 and never think about chemistry again, you'd have to get at least 55 out of 85. So when I say pass, I'm referring to 65% as it always has been in the past. So before we get into some questions, I wanted to give you a few hints for success, and they may already be getting some questions soon here. But first thing is you should be doing some practice Regents exams. Hopefully you've had a chance to do that. They're really all available online. Hopefully you've done some, just get the format down. Secondly, make sure you know how to use all your reference tables, every single one. One of the things that you don't want to keep doing tomorrow is fishing for the table. You should really know where the tables are, where you can find the information you need. Thirdly, there are some acronyms that can sometimes help. They actually can be very useful, but only if you know what they mean. So I brought along some of the ones that I have used. Some of them are better than others, I'll be honest with you. And I shouldn't give myself credit for these. I got these from various sources. For formulas and equations, there's CEM, or even C with an HEM. Charge, energy, mass is what you conserve in a reaction. Brinkelhoff is the symbols for the 7 elements that are diatomic. As far as bonding is concerned, there's some actually really good ones here. BARF is a really good one. When you break a bond, you absorb energy, so there's the BA. Release energy to form a bond, that's the RF. SNAP's a common one a lot of teachers use. If it's symmetrical in shape, it's nonpolar. And if it's asymmetrical, it's polar. TIX is one where if you transfer electrons, it's an ionic bond. If it's covalent, you share electrons. So that's another one that's useful. Hydrogen bonding, the 3 elements that are involved along with hydrogen are fluorine, oxygen, and nitrogen. That spells out FON, like you're having a lot of fun tonight watching this, I hope. Or you've had enough of this. You've had enough chemistry for the year, right? So that's possible too. And then this one came from a student years ago, COMONO. It's actually a way to relate covalent to molecules to nonmetals. So that one's actually pretty useful too. Gas laws, the best one there is PLIGHT, P-L-I-G-H-T. For an ideal gas, you're looking for low pressure and high temperature as the conditions that will help a gas have the most, or be the most ideal. Acids, bases, salts, ABS, that's for knowing which things are electrolytes under the acid-base chapter. Bases accept, acids donate. That's one that when you're involving the alternate theory of acids and bases can help. with H+. Redox has some really good ones here. Leo says GR, loss of electrons, oxidation. Gain electrons, reduction. That's a good one for that. Oil rig is kind of a modified Leo, says GR. It's not quite as useful. It just says loss. It doesn't say electrons, but it still works. Reductions, gain. Anox, anode goes with oxidation. Red cat, reduction goes with cathode. So those are good to possibly use. And I got a couple in the back here. For delta H, you can use potential energy of products minus potential energy of reactants to give you the word pepper with a minus sign in between. And of course, this is an example of a potential energy diagram. You can see the delta H is the difference between the products and the reactants. This is, of course, is exothermic. Not only does it say that, but also because the products have less potential energy than the reactants. And then equilibrium, rec, rates equal, concentrations constant. That's one that I modified from another one I had heard. The rates have to be equal at equilibrium, but the concentrations may not be equal, but they will be constant once you reach that condition. And then here's a couple other ones. Honk 1, 2, 3, 4. Essentially, when you're doing organic molecules, the H should have only one bond. O should have 2, N should have 3, and carbon should have 4. I think for the purposes of the organic molecules, that will work well. Does it work for everything in Lewis structures? Maybe not, but it should work pretty well for the organic chemistry. This last one is just something I made up because that's the order I teach the 7 reactions for organic. It doesn't really spell out a word, but safe skapa sounds like a real word, doesn't it? So substitution, addition, fermentation, esterification, saponification, combustion, and polymerization. Now those words, by the way, are ones that you do have to know by heart. So just in case, you may be asked, which type of reaction or what type of reaction is this? And these are some of the words that they could throw on. So just keep that in mind. Okay, so those are some acronyms that I think are useful. But again, you have to know what they mean for you to use them properly. Tonight you want to get to bed fairly early, although your test isn't in the morning like it usually is. Still, I wouldn't stay up till 4 in the morning studying or doing anything else. Be confident, that's always important. And when you're taking the test, make sure you read all directions and answer all the questions. We want to make sure that every multiple choice is bubbled in and every free response is answered as well. So when you're done with the test, make sure your bubble sheet, you go back and look. Make sure you've actually filled in every bubble because that's just, you can't get a point for something that isn't even filled out. So make sure you do that. And then at the end, of course, you'll sign your paper and go from there. But as far as the bubble sheet's concerned, that's that. A few other things here. Leave nothing blank. Don't, like I said, leave anything blank. Make sure you answer the questions. Hopefully you can come up with something that makes sense. Completely bubble in your multiple choice answers. No partial bubbles. Completely fill in the bubble. Avoid changing an answer unless you're 100% sure it's wrong, because a lot of times people go from right to wrong, actually more so. So only if you're 100% certain it was wrong, then change your answer. And don't try to use every square inch of paper, because on those lines for the short answers, like for example this one, they might give you a lot more space than you really need. So don't feel like you have to fill up every square inch. Some people do, and it's not necessary in most cases. Avoid using pronouns. This is a big one. A lot of people say, for example, the question might be, compare the intermolecular force strength between water and some other molecule, and they'll say something like, it is greater. Now, what does the it mean? Does it mean the water? Does it mean the second molecule? It's not really clear. So you want to say something like, the water has stronger forces. That's really the important thing. So be specific when it comes to that. Never assume you know something. Look it up anyway. I know people have these ideas. Well, I know the symbol of sodium. I know the symbol of potassium, and then it turns out they don't. So just double check. Make sure, because you should have time. 3 hours should be good for that. Make sure you use specific info the question is asking about. There's always going to be several questions that'll say in terms of, so make sure you mention those ideas. Use your calculator to avoid simple mistakes, but be sure to type in the numbers correctly. If asked to compare, make sure you use terms such as less than, greater than, or equal to. You don't want to say different. Some people get vague and they say, well, the strength is different than the other thing. But what does that mean? What does different mean? So you want to use things like less than, greater than, or equal to. Determine, if you see a word or a question, say, determine the gram formula mass of water. That means you're going to do a calculation usually, if not always. For a numerical setup, make sure you show the placement of numbers. Don't just put a formula that has no numbers in it. And don't solve it either necessarily. Make sure you have that in place. Be careful rounding your answers also, because you don't want to round incorrectly. Like, for example, the formula, the atomic mass of something. You want to make sure you do that correctly. Make sure your math answers make sense. Sometimes the math answers people get, like I was doing a practice test last week and somebody got a molarity that was so large, I mean, I'd be scared to be 10 light years away, honestly. It was that high. So please, have numbers that kind of make sense. Molarity shouldn't be more than, even if it's 5 mole or something like that. Sounds like we're getting a question here. So I'm just going to wrap up this page, and then Carson's going to, or maybe not. Carson thought he had a question. They hung up. Okay, well. Probably not the best way to ask a question, but hey. Watch for words such as not, except, and least. Like, for example, if they say, under what conditions is a gas least ideal, then you don't want to use the plight perfectly. You want to go the opposite. So be careful with that. Don't overlook and overanalyze the easy questions. There actually, believe it or not, are a lot of easy questions that they repeat over and over again. These two gentlemen can say the same thing. After taking AP this year, Regents, of course, seems like a lot easier than that. So they really are. A lot of them are straightforward right off the reference table. Skip over the tough ones and go back. And then if you're completely unsure, sometimes you can, like of a multiple choice, you can sometimes see which answer is different than the others. So sometimes that can work. And then 2 other things here. Write legibly, clearly, and large enough, or largely enough. Some people write teeny tiny. We need a magnifying glass. You have to remember the graders are older than you are. And some of us might need reading glasses either currently or close in time. So try to avoid us having to get the really thick reading glasses. And then check your work too. You don't get a special prize for being the first one done. So remember, you're going to have to stay there 2 hours anyway, so you might as well take at least as much time as that. So those are some things there. Anything yet on tweet? Nothing yet? Okay, so I'm going to keep going. I have some other things to think about. And again, feel free to tweet or call in some questions, and I'll be happy to interrupt this intro stuff that I have to answer your questions. So if you think of anything that pops up, and I put down some helpful hints here that might help tomorrow regarding let's just say some mistakes that I've seen students make in the past that I don't want to see any of you do tomorrow. For example, when you're balancing equations, never use 0 as a coefficient. Because if you put a 0 in front, that means that the substance isn't even there. I guess that would be true, right? If you put zeros in front of everything, it's not there, right? So I guess that would be balanced, but you won't get credit for that. So don't put 0. Okay, 1 would be the lowest whole number you would use. Hydrocarbons only have hydrogen and carbon. Clearly from the name, hydro, hydrogen, carbon, carbon, there you go. So again, sometimes you can break down the words and you can get something from that. This one right here, remember this third bullet here? This one gets students every single year. Hydrogen bonds are actually not types of bonds at all. So if they ask you a question about types of bonds, never put hydrogen bonds ever. Ever, ever, ever. I can't say ever enough. Never, ever. Because it's not. They're actually a type of intermolecular force, which is actually weaker than a bond, but is significant when it comes to physical properties, such as boiling point of, say, water. So those do come into play. The difference between ionic and covalent is often mixed up. Ionic is generally between metals and nonmetals. You'll have one of each usually. And covalent will be between nonmetals only. Some other things that I see people do sometimes, mixing up words that sound similar, like isotopes and isomers. They are completely different. Isotopes have to do with the nucleus, the number of protons and neutrons. The sum of those may be different in different atoms of an element. But isomers have to do with organic chem. So we're talking about a completely different unit, really. Electrons move from the excited to the ground state. That's when you get the light emissions, the lines that you see sometimes in these questions. Here's one that I see occasionally when people calculate atomic mass. Never add up the individual masses and then divide by the total. Because the thing about atomic mass is that it's a weighted average. That's why. The individual isotopes don't have exactly the same percentage of abundance or how much in the world. So because of that, you can't just divide by the total number of isotopes. It doesn't work that way. For Le Chatelier's principle, for the short answer questions, you can generally just say what direction you're going to shift the equilibrium, either left or right. Here's a few things on oxidation and reduction. Oxidation and reduction are commonly mixed up. Oxidation, you're going to increase the oxidation state, and electrons are written on the right side of the arrow with a plus E minus. Make sure you do that. Reduction, you do the opposite. Electrons are written on the left side, and also you would, again, you would add them on the left side, but the oxidation states will actually decrease from start to finish. Voltaic cells versus electrolytic. Voltaic cells are spontaneous. You convert chemical energy to electrical energy. You don't need a battery for voltaic, whereas electrolytic, you do. Those are the non-spontaneous cells, and those convert electrical back to chemical. Okay, a few more things here if we don't have anything yet. So I'll just do a few more things, and then we can look at some more topics that come in. Catalysts, one of the things that students mix up is that they do lower activation energy. Some people think that raising it actually speeds up a reaction, but when you lower activation energy, that will actually speed up the reaction. It looks like we have a question here. So I'm going to postpone going over this first.
Thank you. We'll get your question.
Okay, so Carson got a question. So who we got here, Carson?
All right, so Courtney from Whitesboro wants to know the difference between an isomer and an isotope.
Isomer and isotope, yes. Let's go in a little more detail here. Good question, Courtney. I think I know who you are. I have a Courtney in class. So isomers are, you're looking at organic structures. Okay, so we're looking at molecules with the same molecular formula, but different structural formula. So, for example, you might have a molecular formula. We can take an example from a reference table here. So let me grab one of my several copies that I brought in case I have to write all over these. There are several tables here about organic, and this one, these two right here come into play. Tables P and Q. Let's start with Q. Let's take a formula. So when we say general formula, that means the overall carbon number and hydrogen number. And for these various types of hydrocarbons, there's always a pattern. The alkanes always have a pattern CN, which means whatever number N you want to call it, whole number. And then for the H, it's 2N plus 2, so you double that number and you add 2, like C5, and then it would be H12, for example, if you plug in N as 5. Alkenes are, you just double the carbons to get the H's, like C5H10. And then the alkynes, you would double it and subtract 2, like, say, for example, C5H8. So when it comes to isomers, let's start off with these hydrocarbons. Let's just do an easy one. Let's say you had C5H12. Okay, we'll do an alkane. Okay, so in the case of these isomers, you could have multiple ways of drawing C5H12. So how can I do that? Well, in this case, being that it's alkanes, notice the example here. If I move this up here, you can see that it has single bonds between the carbons, right? So the single bonds mean that it's a saturated hydrocarbon. And being saturated, there's no more room to squeeze in any more H's. There's no way. You just can't. You can't squeeze in another H. There's the max number right there. But are there more than one way, or is there more than one way to actually draw this? And the answer is yes. The easiest way to draw this would be to say, okay, 5 carbons, single bonds. and just connect them with my single dash, which really means 2 electrons, or 2 dots if you use Lewis structures. And then I would put the H's all on the outside. These would all be H's out here. And you can draw the H's in like this. And there are shortcuts, obviously, you can use. Some people don't even bother putting the H's in. I recommend doing it for the purposes of tomorrow, only because if you don't, you might leave out a bond that you actually need. I'm just going to make this a little bit smaller so we can see the whole picture, because clearly it's an award-winning diagram, right? Wouldn't you guys say? Yeah, see, they agree. But this one right here is 5 continuous carbons, and so because of that, the name is actually real simple. This is just the prefix for 5 is pent, and being that it's all single bonds, you would call that pentane. However, in the case of C5H12, you can actually draw it another way too. You could actually draw, say, 4 carbons in a chain. And then what you could do is actually draw the additional carbon off of one of the middle ones, like that. And then you can put your H's on the outside, and you'll see that actually this one has the same number of H's as the original one. I'm trying to squeeze this in here. But it turns out it's not the same molecule. In fact, it'll have different properties and everything. And so the name is different because you don't have a continuous chain of 5. You can't call it pentane anymore. However, instead, you can call it really 4, which is butane. And then you have to account for the fact that there's this little branch, like the branch on a tree, right here. You have to name that part separately. So that would be called what 1 carbon is. Prefix for 1 is meth, so you would call it methyl. And then the name of the main chain is butane. And then one last thing you always have to consider is, okay, that side chain, that methyl group, is that in a situation where it could have been in a different spot where you may have to specify which carbon it's attached to. It's not a bad idea to put in a number just in case. You don't want to put in the wrong number. The number, I mean, which carbon is that branch attached to. So you would number your carbons on the main chain, 1, 2, 3, 4, or 1, 2, 3, 4, either left to right or right to left, whichever gives you the smaller number for the location. In this case, counting backwards is actually better. 1, 2. So if you were going to put the number in, you would say 2-methyl butane. Now, some of these you can get away without putting the number in, but it's not a bad idea to think about including it, but as long as you do the lowest possible number that could be there. Now, so isomers, again, they have the same, they're both, in this case, both C5H12. Let me zoom out some more so you can see both together. They're both C5H12, but they're different. They're actually different names, different structures. They have different properties, too. Their boiling points won't be the same, their densities won't be the same, etc. What will be the same, though, is their molecular formula, their molar mass, their percentage composition by mass, things like that will be the same. So those are isomers. So this is from Courtney's question. And then isotopes, to clarify that, isotopes are situations where you're looking at the nuclei of elements, where now you're going to look for different atoms of the same element, or atoms of the same element. And then with that, they'll have the same number of protons, but a different number of neutrons. So what that means is this. If you take a common element like nitrogen, for example, which is 80% of the air, roughly, nitrogen is not all the same. Not every atom is exactly the same. What is the same, though, is the atomic number. So if you look at the atomic number here, you'll see that there's a 7 there. That 7 tells you that you have 7 protons for every nitrogen. However, this number in the upper left corner, you'll notice it is not a whole number. It's the atomic mass actually has a decimal, several decimal places after it. That's because it's an average. So what that's saying is that there are multiple forms of nitrogen. Now, one form is nitrogen with a mass of 14. Let me move this back. Oops, I think I was zooming in instead of out. Sorry about that. I was just testing all of you. Nobody said anything. I was testing the students here. I was testing all of you at home. Nobody said a word, so I guess you don't pass that test. But these right here, these are the two most common isotopes of nitrogen. And what the 14 and the 15 are, those are the mass numbers. This is the sum of the protons and the neutrons. And so you can see the one on the right is a little bit more massive. But both of them have the same number of protons, so that'll be still 7. So when you subtract the 7, you'll get 7 neutrons. Here you'll get 8 neutrons. You can see the one on the right has more mass. But the protons are still the same. The protons are still 7. Because remember, the protons determine the element. That's the identity. It's like the fingerprint of the element. Okay, well, thank you for that question, Courtney. It sounds like we have another one here. What do you have, Stevie?
We have Anthony from Whitesboro, and he asked the difference between fusion and fission.
Fusion and fission. So a nice little nuclear reaction to move on to. So I'm going to go back to the Elmo here. So fusion and fission. So unfortunately in chemistry, there are sometimes words that are used multiple times, and fusion is one of them. So in the case of fusion, if we're looking at nuclear reactions, we sometimes might even refer to it as nuclear fusion. That way we don't confuse it with the other fusion, which is melting, which is a physical change that we see all the time. But nuclear fusion happens naturally on stars, and it's a lot more complicated than I'm going to tell you tonight. But really the big thing to look for with fusion is the combination of hydrogen plus hydrogen to give you helium. And there's a lot of ways that you'll see this. You'll likely see the mass number and the atomic number here. But it might be something like 1/1, maybe a 2/1, maybe a 3/2. This is just an example. There will be slightly modified versions that have neutrons as, say, a neutron's a product. But for the purposes of this test tomorrow, that would be the one that you would run into. But you got to be careful because we have seen questions where they've had hydrogen and helium, but it wasn't actually fusion. You have to be actually adding them together because you're fusing them, right? You're fusing the nuclei. And one of the things, of course, that the big purpose of this, why this could be useful on the Earth if we could ever figure out a way to do this safely, is you get a lot of energy out of it. And so the energy comes from the fact that some of the mass in the nuclei is converted to energy, and that happens in nuclear processes. Even though technically these numbers, 1 plus 2 on top adds up to 3, and 1 plus 1 on the bottom adds up to 2, technically there is a discrepancy there. They're not really exactly the same. We round them off just to make it convenient, but the mass that is not conserved, so to speak, is converted into energy, and in the case of the sun, that's what helps heat us up. So we should be thankful that we have that. But other stars do the same thing. And then, in Earth science, you may have learned about other fusion, but this is the one that you'll see on the test. Fission, on the other hand, is something that we do use on this planet. This, of course, actually, yeah. I'm going to go back to fusion for a second. Think of fusion as small to large, small nuclei to large nuclei. One of the things that they've been asking a lot recently is, in terms of nuclei, why is this a fusion or a fission reaction? So it might be good to think in terms of that. In the case of fusion, you're going from small to large. In the case of fission, you're going from large to small. And there's a couple things you want to look for with fission. Probably the easiest one to look for is really not necessarily the answer they're looking for on the Regents. And that is with fission, you need a neutron to kind of get the process started. And so you'll see a neutron, which is 1/0n, that's the symbol for neutron, plus something else. It could be uranium, it could be plutonium. Some isotope of uranium, like 235, is the one that's able to go through fission over 92. And that'll give you, in some cases, you might get krypton, you might get barium. There's different versions of fission. I forget all the numbers, but the big thing here with fission is that you're starting out that you have this larger, uranium is quite large. I mean, uranium is element 92. I mean, that's a big element. But barium and krypton are much smaller. 56 protons for barium, only 36 for krypton. And so you're going from large to small. But the other thing you want to look for is more neutrons on the right side. So it's like, say, like 3, 1 over 0 n as products here. So that's the thing you want to look for. The neutrons are on both sides, but as far as the questions are concerned, you may have to say large nuclei are split into smaller nuclei. That's a lot of times what the questions will ask. Even though the neutron part is correct, it may not be what they're asking for. All right, so thank you, Anthony, for that. Sounds like we have another question. Carson?
All right, so Skylar from Whitesboro asked what a forward reaction is.
So Skylar from Whitesboro asked what a forward reaction is. Yeah, I mean, this is a really good question that we often overlook. Sometimes you see that in a question. So a lot of reactions go in two directions. If you have element A or some substance, A could even be a compound, and then that becomes some other substance, let's say it goes to D. A goes to D, and it might stop. And then in some cases, D might go back to A, so you have this reversible reaction. A lot of times you'll see the arrows written like this. They kind of leave off part of the arrowhead. But in that case, that's a reversible reaction, which has the capabilities of reaching ultimately an equilibrium scenario. Forward just means the left to right direction. So this direction is forward. And then the other way is reverse. Okay, so hopefully that answers your question, Skylar. Thank you for calling in. Okay, nothing yet. So while we're waiting for any tweets or anything, no tweets. Hopefully the Twitter and the phone are available for anybody who's watching this. Feel free to call in or tweet any questions that you have. And again, this is Regents Science Live. I'm here from Proctor High School, and I have Stevie and Carson helping us out here. Joe in the back. Thank you, Joe, for doing all the electronics and all the setting up here in this really cool studio. I have to say, this is a neat place to be in right now. So what I do want to do is go over a few things while we're waiting for some other questions here. The next bullet, I did talk about this earlier about catalysts lowering activation energy. That is something that sometimes students do mix up. The reason why catalysts speed up reactions, that's really the best way to word your answer. They lower the activation energy. It makes it easier for the reaction to take place. So if you think about a potential energy diagram, the graph might look like that for an exothermic reaction, but you're lowering the height of the mountain, so to speak, with a catalyst, and that will speed things up. Sounds like we have a question here, so I'll postpone this again and let them ask
Sure.
a question
Thank
here. Stevie forgot to ask what school it is, so we'll just pretend we know.
Actually, she told me.
Oh, she did?
This is
Yeah.
Caitlin from Proctor's question.
Okay, Caleb from Proctor. So nice to have a different district here calling in and right from your home school. So go ahead.
And she asked to go over Le Chatelier's principle.
Le Chatelier's principle, yes. This is always a question that pops up on these. Okay, so Le Chatelier's principle is interesting. It really works for equilibrium. Okay, so whenever you're in an equilibrium situation, and a lot of textbooks try to make this more complicated than it really is. Here's the way it works. I'm just going to kind of use more simple kinds of terms, stuff like that. If we mess up equilibrium, the reactions will correct themselves to get back to equilibrium. That's just another way of thinking about it. So, you hear all these things about, if the system the equilibrium is affected by a stress, then obviously it has to fix itself. So I'm just going to say if we mess up equilibrium, the reactions involved will correct themselves to get back to that equilibrium state. Now, with this being said, when we say back to equilibrium, it doesn't mean we're actually in the same exact equilibrium state we were in before. But keep in mind what equilibrium means. There's two things you need for equilibrium. So let's go back to this thing I just did a minute ago with A becoming D and vice versa. Two things you have to have for equilibrium. You have to have a reversible reaction where the rates are equal. So I'll say RE, this is that little acronym I did earlier. Rates are equal, and the concentrations of reactants and products have to be constant concentrations. Not equal to each other, but constant. So if we're at equilibrium, for example, if you looked at a graph, concentration versus time, A and D would have level constant amounts, but the heights of them are not the same as each other. So again, that is considered to be constant. Now, when we have Le Chatelier's principle involved, we might screw these up. I might raise the amount of A and decrease the amount of D. And when that happens, when I get to the point where they're not equal anymore, not constant anymore, now we're in this stressed out situation, but then it has to correct itself to get back to equilibrium. And so to finish up your question, I just wanted to point out the various stresses that could actually affect the equilibrium. I know we have another question that just came in. So let me just quickly do this. Let's say we have A as a gas plus B as a gas gives you C as a gas plus energy. And let's just take, for example, some of the stresses that you could run into. So let's say if we add more A gas. So if we add more A, what's going to happen is I have too much A. So if I increase the amount of A, I have to get rid of the excess. And so what's going to happen is I'm going to shift in the opposite direction to use up or consume the extra A that I need to get rid of that I shouldn't really have. It's kind of like walking in your house one day and you have way too many packages of cookies in your house. You're just going to have to eat them all, right? Is that true for you guys? You get that sometimes? You walk home and there's 10 packages of cookies right on their bed, actually. And then they have to eat them all, right? So you have to shift to the opposite side to get rid of the extra A. And so you would just say, shifts right is really, honestly, what you can oftentimes get away with, explaining your answer. If it says in terms of Le Chatelier's principle, explain why the A will go up or B will go, that kind of thing, you can often say which direction you shift. Another stress you could have is temperature. If we raise the temperature, and hopefully we all remember that temperature is average kinetic energy, and that means that if I raise the temperature, I could raise the energy over here on the right, and so if I increase that, this time I'm actually going to shift the other way because I have too much product, so it's actually going to cause me to shift that way. So that would say shifts left for that example. Okay. Let me move that up so you can see it. And then the third stress we could say is temperature. If we raise the temperature, pressure. Thank you. See, I'm testing. These guys got it right this time. I meant to say. If we raise the pressure, he gets an extra bonus point, although those grades are already done. If we raise the pressure now, and you have to remember that pressure is really only affecting gases. So we would have to look at the number of gas particles on each side of the equation. So in this case, the left side has 2 gas molecules. I have one A and one B. And the right side only has one mole of gas, so to speak. Well, 2 is greater than 1. And so what happens is if you raise the pressure, you end up shifting toward the side with fewer molecules or moles of gas, if you look at it from that standpoint. So it'll be shifts right. And the logic behind that is if you raise the pressure, what you're really doing is you're squishing the container together. You're actually squeezing it, lowering the volume. And so the reactions will automatically take place faster one way or the other to kind of relieve that extra pressure. Now, just to clarify one last thing, when we say shift, all it really means is that temporarily one of the reactions occurs faster than the other. And then eventually they will become equal in rate. That's the thing that shifting. Shifting just means temporarily one of the two, left or right, occurs faster. The other thing, too, is if you have to say which direction you shift, never say left to right or right to left. Just say left or just say right. Don't get it too complicated there, because then it's like, okay, well, do you mean left or do you mean right? So sounds like but thank you for your question. Who's next here?
All right, so Carly from Whitesboro asked what the difference between an exothermic and an endothermic reaction is.
So thank you, Carly. difference between an exo and endothermic reaction in general. Okay, so exothermic, and then there's endothermic. So to simplify matters, we're just going to kind of say this. Exothermic, we're looking at release of heat, or release of energy. I'll say energy, heat energy essentially. And then endothermic, absorption of energy. That's really the easiest way to think of it. And that's really the overall release or overall absorption is what we're looking for. So in the case of exothermic, the reaction might be written out like this, where we have A plus B gives you C plus energy on the right side. And then in the case of endothermic, it might be A plus B plus energy gives you C. So in the case of the endothermic, I'm absorbing some energy, and it's on the reactant side. In the case of exothermic, it's being released. So think about it this way. If you were looking at an everyday example of something that's exo and endothermic, a good example of exothermic would be something like a heat pack that you might put on an injury. Because heat packs, what you're trying to do is warm up the body. So there's something that's placed in water, and a lot of times when you put stuff in water, there will be heat released. And so that heat, of course, then can be used for your body. In the case of endothermic, a cold pack actually works like that too, where they mix something with water that actually absorbs energy and it actually makes it cooler. One last thing here with this, and while we're on this, is those potential energy diagrams understand the difference between the two. This is PE on the y-axis, and then the x-axis, they call it the reaction coordinate. It's almost like time. And so in the case of exothermic, you start with a fair amount of energy potentially for the reactants. You absorb some, that's called your activation energy. You then release a bunch of energy, and then you end up with less energy than you started with. So again, you're releasing energy to the surroundings. So there's less in the material that you're using. This difference between the reactants and the products here, it's an R and a P. This difference right here is your delta H, which is your heat of reaction. That's that PEPPER acronym I used earlier, potential energy of products minus reactants. Because the products have less energy, though, this is negative. In the case of the other curve here, the endothermic graph, it's exactly the opposite. You start low and you end high. In this case, delta H is positive. And so the products have more energy than the reactants. So therefore, you're absorbing more energy and so on. You could argue that, if you look at it, both reactions absorb some, but the thing is, in the exothermic, you're releasing a lot more. So there's an overall release, essentially. In the case of the endothermic, you're absorbing a lot more than you're giving off at the end. So again, the definition at the beginning is really an overall release for exo, overall absorption for endo. Okay, hopefully that answers your question, Carly. Thank you. Sounds like we have another one.
We have a two-part question
from good.
Matt from Whitesboro.
Matt from Whitesboro.
He asks, can you go over Lewis dot diagrams?
Mm-hmm.
And he also asks for your NBA Finals pick.
NBA Finals pick. Maybe like who I think is going to win? Boy, that's a tough one because these games have been tough. Probably Golden State, but I don't know. They're up 3-2. It really depends on tonight. If they lose tonight, we'll see. But that's my guess, but I don't know. I know a lot of Celtics fans, so I don't want to make them upset that I even said that. So I'm not a huge basketball fan for anybody that's watching this that doesn't know me. Lewis structures. Yeah, Lewis structures are interesting. There's the ones that you're going to have to do most likely. You're going to have to draw something, a covalent molecule. And the way to do that is using your periodic tables. Let's do an example of one that is relatively simple that you could see, I suppose. Let's do N, let's see, nitrogen with 3 fluorines or something like that. NF3, something like that. So how would you set something like this up? So what you do is you take your periodic table and you find the valence electrons for each element. Now N, if you look carefully here, you see this 5 right here. This 5 means that there's 5 valence electrons. In the case of F, you have 7 valence electrons. Oops, I went too far. 7 valence electrons, right? So 7 for fluorine, but 5 for nitrogen. So what we do when we're dealing with covalent bonding here, we add up all the valence electrons. And some people try to specify, okay, this one came from the N, this one came from the F. For me, I've always just done it where you just add them up. There's different ways of teaching it. You can use X's, you can use dots. I just use dots. That's just, so if anybody here is watching this uses the X's as well, that's perfectly fine. N has 5, F has 7, but there's 3 of them. 3 times 7 is 21, so add those up, you get 26. So the thing about this one is you're going to have 26 electrons. Your final picture has to have 26 electrons. And so you have a choice in how to do this. You can do it, so I would put the single element in the middle, in this case N, and then you could surround 3 Fs like this. And then what we would do is we would simply start off with a pair of electrons between the atoms that are, they're sharing electrons in the middle there. So you can put a pair there, and a pair there. And then remember that each element, when you're doing a covalent bonding, Lewis dot diagram, each element is going to have 8 electrons around it by the time you're done, except for hydrogen. Remember, hydrogen is only capable of having a total of 2 ever in a diagram. So just keep that in mind. But to fill this out, N only has 6 around it right now, so I got to put 2 more on it. And I'm going to do that by just putting a 2 on top. And then all the Fs are going to need electrons on the outside. And again, I just add them all up. Some people use X's for one element, dots for the other. But if you add these up, you should get a total of 26 electrons, and that should work for that particular molecule. Also, what you can do is use dashes in between. Each bond that is 2 electrons you can draw as dashes. And so then you can put, for example, these out here. These are probably the 2 most common ways of doing it, either this one or this one. But there are other ways you can do Lewis dot diagrams. I know we're getting another question. I just want to mention one other thing with this, and that is, what if you have to deal with double or triple bonds? And so a good example of this is nitrogen, N2. N2, which is found, like I said, in the air, 80% of the air is nitrogen. We saw from above that nitrogen has 5 valence electrons, and there's 2 of them. So 2 times 5 is 10. But the problem is, if you try to put 2 electrons only between the ends and try to put the 8 around, this is not going to be correct because you have too many electrons. You've violated the number. You can't just magically add more electrons just because you feel like it. You don't want to know the penalty for doing that. It's pretty bad. So instead, what you have to do is actually put more electrons in between the atoms. In fact, 6. And then you put the others out here. And that'll add up to 10, but each atom is surrounded by 8. There's 8 there, and there's 8 there. So it actually will work well. This also can be drawn as a triple bond as well. So either way is perfectly fine for that. And this one might be a good one to memorize. They do ask that question a lot about nitrogen. But those are a couple of examples of Lewis structures. Again, add up your valence electrons, and then make sure that at the end you have that correct number. If you need to use double or triple bonds, that may be necessary. Sounds like we have another question. Thank you, Matt, for that question. Go ahead, Carson.
Yes, so Ava from Whitesboro asked if you can make dollars and cents of Safeskapa?
Safeskapa. She asked me if I can make dollars and cents. Yeah, I don't know where she got that joke from. Safeskapa, all that is really is just, Ava, thank you for asking here. Again, for those of you that maybe have just popped on, you can tweet or call in. The information is on your screen. We're at Regents Science Lab. We're coming live from Proctor High School. Safeskapa, all it is, Ava, is just a list of the 7 organic reactions that you should be aware of. And I can just highlight some of these. So the first one is substitution. A lot of people have different ways of putting these in order. This is just the order I teach them. So if there's any teachers out there that are like, Safeskapa, that's not a word, I get it. But that's just the order that I teach the 7 reactions. You could do other orders as well. Substitution means you are simply replacing one atom with another, a hydrogen with, say, like a halogen, for example. So in this case, the methane, which is right here, you could add, or you could substitute in a chlorine atom. And so what that would do is you get a Cl in place of one of the H's, and then you would get HCl as your other product. The thing about substitution is you're always going to get two products. That's the thing about substitution. You got to get two products. If you only get one, it would not be substitution. Okay, so substitution is two products for that. The A here stands for addition. Addition, of course, means you're literally adding two things together. So we would take something that has, say, a double or a triple bond, like ethene, for example. And if you're adding something to it, like chlorine, the chlorine will actually essentially break apart to two atoms, and then it will attach itself one to each of those carbons where the double bond was. So this now becomes a single bond. That's the other thing you got to remember. This becomes a single bond now. The chlorines will then surround where the double bond was, and then the H's just kind of fit into place like that. So that's addition. You can see the difference. Substitution, you get two products. Addition, you only get one. The F stands for fermentation. There are a lot of different types of fermentation, but in this case, the only one that you would run into is the production of ethanol. But most of you watching this tonight probably don't know what that is. You're not 21 yet. So if you're confused, I understand. But glucose, which is a simple sugar, can get broken down into, with the help of an enzyme from yeast, ethanol, C2H5OH, plus CO2, which is the bubbles that we sometimes experience, perhaps. But again, you wouldn't know that until you're 21. Is that correct? You guys, they don't even know what it is over here. So and they already took AP Chem. They still don't even know. Esterification is the E. That's the production of an ester. Esters are chemicals, or actually they're natural and artificial, that oftentimes have fruit-flavored smells to them. Esters have, oops, I got to get the right table here. Table R, we need to look at this right here, the C double bond O with the other O next to it. Esters have that. And you can always tell if you've drawn an ester correctly because your paper will now smell like fruit or something, or some other ester smell. So if you did it right, you might get the smell of a pineapple or the smell of some other, right? So they can confirm here that that's what you get if you draw an ester right. But really the reaction is an organic acid plus an alcohol gives you an ester plus water. So the acid, I'm just going to simplify this a little bit. The acid has a special, what's called the carboxyl group, COOH, and that'll combine with the alcohol here. And you essentially are pulling out water when you do that. And the rest here is H and stuff. And so then you end up getting your ester linkage, and then you get water as a byproduct. So that's the thing. You're actually getting, you have a couple of OHs there on the edge. The acid has the other O as well, but you get those two together and you can pull out water. That's actually one of the harder reactions if you had to draw anything from it. They have done that before. They've actually asked people to draw either the alcohol or the acid, but what's nice about it is usually they'll have the ester already drawn, so you can kind of pull out the pieces on what's on the right side and then make sure the left side has the same atoms as well. The next S stands for a word that is hard to spell, but it's kind of a cool word. It's the Ponification. There's really not much to this other than soap is made. So just remember soap. The reaction itself is pretty complicated, so you would not have to draw that out. C stands for combustion. And combustion, you probably are a little bit familiar with what that is in general. But for example, if we were combusting propane or something, propane, you would have put in some oxygen, and you would get some CO2 and water. Now, this is the most common type of combustion you would run into in this class. There are other types as well. But you're going to get CO2 and water. That's really the key with that. And actually, a lot of these are listed on your reference table I. They're actually already there. So if you look at table I, the first 6 reactions or so are the same style of reaction. Let me zoom in on this so you can see it better. All these, and you'll notice also that they're all exothermic. See that? Every single one has a negative delta H, so they're all exothermic. They all release energy, which we would expect. It wouldn't make sense to burn, like, for example, the third one down, octane, and not get energy out of that. Same thing with propane that you may have for your gas grill. So combustion, that's really what to look for there. And then finally, the last one, a couple ways you might have heard it pronounced, polymerization or polymerization, is just making of long chains of molecules. And the drawings can get complicated, but that's all it really is. A lot of times the question might talk about a whole bunch of molecules that are or atoms that are put together and they just make the chain thousands of times long. That would be the polymerization. So a polymer is just a long chain of repeating units. So plastics are some artificial polymers. There's also natural ones too, DNA, things like that. So there's a lot of natural polymers as well. But this is, we often think of plastics for polymers. Anything coming through yet? Okay, so hopefully that answers your question, Ava. That was the safe SCPA. So I'll kind of zoom out so you can see them all at once. Maybe can't quite fit them all, but that's essentially safe SCPA. All right. So let me, while we're waiting there, I'm going to go over a few other things here that often are mixed up. And this might trigger some more questions, too, that people have. And that is so I had a few more things on here. One is don't mix up chemical formulas with chemical names. I think one of the things that people, when they read questions, sometimes don't answer the question because they're not paying attention. A formula would be like H2O, right? Or CO2 or something like that. Whereas a name would be like carbon dioxide or something like that, the actual name of it. Of course, water, as we all know, we call it water, but really it technically would be dihydrogen monoxide. So if you really want to scare somebody, be like, hey, I need to go to the store to buy some dihydrogen monoxide, and people might get scared. But that's one, be careful not to mix those up. Another big one not to mix up is bond polarity and molecular polarity. Those things are so often mixed up. The bond polarity, you're looking at electronegativity difference. You have to actually subtract the values, and the larger the difference, the more polar it is. Molecular polarity has to do with shape. That's that symmetry I talked about earlier. And so something like water, for example, is polar. And the easy way to remember that is that polar bears have to drink water because they will dehydrate themselves if they don't. I know because I used to have a couple as pets. But molecular polarity as shape, that is something to be aware of as well. Not the exact same thing necessarily as bond polarity. Next one, don't mix up chemical and nuclear processes. We already talked about fission and fusion, but chemical processes like single replacement, double replacement, synthesis, decomp, all those organic reactions, those are not nuclear reactions. So you don't want to be talking about mass is converted to energy when you burn this piece of wood outside your house. I mean, that's not going to be close to what we're talking about. So be careful not to mix those up. Another thing not to mix up are the two formulas that will allow you to get molarity. Now, this formula right here is used for titrations, and probably all of you did a titration in class where you use either a burette or a syringe or something, and you dripped in slowly an acid into a base or vice versa, and then you added an indicator such as phenolphthalein or methyl orange or something, and then it changes color as you add just enough of the acid or base. And of course, this formula is right on the back of the reference table. However, there is only one correct way to pronounce it. So as we all know, it's pronounced mava equals mba, but some people don't always pronounce that. These two gentlemen here, of course, know to pronounce it just like that as well. This formula is relatively straightforward to use. Just make sure you're lining up the acid stuff with itself and then the base stuff with itself as well. Occasionally they will, it's been a long time since they've asked any tricky ones on this, but theoretically they could. Sounds like we're getting another question here, so I will hold on a second. Two questions we got. Wow, this is double duty here. So what do we got first here?
The question's from We Are the Harrys on Twitter, and it says, can you go over balancing equations?
Balancing equations, yes. Well, thank you for the question here. Yeah, balancing equations. So balancing equations in this class is not what it might be in college. So there's really not going to be anything too crazy. So for example, if we had H2 plus O2 gives you water. So one of the things you got to be careful with is that when you balance an equation, if you leave the coefficient blank, so what you put on the line is a whole number. The number you put on there, if you don't put a number in, it's assumed to be a 1. So keep that in mind. So you're allowed to leave it blank if you're confident a 1 works. Otherwise, you have to put a whole number, and don't put 0, as I said earlier. 0 is always going to be incorrect. Even though if you put zeros across, obviously it's all balanced, right? There's nothing there. But now what you do is don't make it any harder than you need to. Look at each atom individually and try to balance that atom first. So for example, I'm looking at the left side here. See that little 2 right there? That 2 indicates that I have 2 H atoms, but the 2 there means I also have 2 H's there. So those are already balanced. I don't want to touch that. Here, I have 2 oxygens on the left, but on the right, I only have 1 because there's no subscript there. So what I do is I have to put a large coefficient 2 in front, which means now I have 2 molecules of water. By having 2 molecules of water, I really have, if you think about it, 2 oxygen atoms, right? But because I now put that 2 in front, I actually screwed up the H's. It's kind of like getting work done at your house, right? They might have to make a mess first before they can correct something, right? So that we have to make a mess of the hydrogen, but now we have to correct it on the other side. Now you just put a 2. Now, this brings us to a good point. Make sure when you're done balancing, the coefficients cannot be reduced any further. So right now, you really have 2, 1, 2. You cannot reduce a 1 or a 2 because how do you reduce a 1 without going to fractions? Fractions are never allowed in this class as far as coefficients are concerned. They will not let you put 1/2 as a fraction, unfortunately. But just knowing that, 2, 1, 2 is the simplest we can get. What if instead we were thinking outside the box and we said, okay, 4H2 plus 2O2 gives me 4 waters. I mean, is that balanced? Absolutely. I mean, I got 8 hydrogens and 4 oxygens. Everything's good. But it's not the lowest whole numbers. See that? A 4, 2, and a 4 is not the lowest whole numbers. Those have to be reduced. You will not get credit for that. Even though, theoretically, it's a valid equation. It's like doubling a recipe in cooking. That's the thing about balancing equations. You're really coming up with the recipe to make your product. So you have a 2-to-1 ratio of H to O to make 2 moles of water. 4 to 2 is really the same ratio. It's just that that's not acceptable for a balancing, unfortunately. Now, we can do another one here, maybe a little bit more challenging. You have a question too, Carson? We have 2. Okay, so let me just do one more balancing, because this one's pretty easy. So let me do another one that maybe is a little bit more complicated. Not crazy. You're not going to have one that's really awful, to be honest with you. It's not going to be that bad. But let's say you had Zn plus... actually, no, I'll do this. Al plus Zn Cl2 gives me AlCl3 plus Zn, something like that. A little bit harder because now the only element that's not balanced is the two chlorines versus the 3. Now you have to think about how can I make that the same whole number? And the best way to do that is to come up with the number 6. So if I have 2 on the left, I can multiply that by 3 to get 6. 3 times 2 is 6, right? Because it multiplies through. And then I can put a 2 there to make 6 as well. But now, again, I screwed it up. Now I got to fix the Zns by putting a 3 there and then put a 2 in front there. So yes, that would work just as well. But a little bit more complicated, but it still works pretty well. So balancing, think small whole numbers. Okay, if you're really stuck, try a 2 or a 3. I wouldn't start with the number 25. I really wouldn't. Like it just start. I mean, these guys would agree. start with a small number. I think the highest they've had in the last 10, 12 years, maybe the number 6, really. But that wasn't even that difficult a question. I think most people figured it out pretty well. So thank you for that question. Again, for those of you that just might have come in, we are on live from Proctor High School, Regents Science Live. We're still accepting some tweets and calls. We had a couple right here. Carson's next here. He's going to share that.
All right, so Skylar from Whitesboro again asks the difference between polar versus nonpolar.
Okay, so again, with polar versus nonpolar, there's two different types to think about. If we're looking at bond polarity, then you got to think about electronegativity difference. Okay, so the greater the electronegativity difference, the more polar the bond. Okay, so here's the way you got to think of it. When we say something is polar, it's almost like there's a pull, polar pulling. It's like tug of war where one side is pulling harder than the other. So we have to, electronegativity has to do with attraction for electrons. So if I'm an atom and I have a high electronegativity, then I'm going to attract electrons pretty strongly. Now, if Carson has a low electronegativity, he doesn't even care about electrons. He's just going to go off and read his tweets over there and not worry about electrons, right? So in this case, we're looking at table S. We have to use the actual electronegativity values right on here. So we might want to compare, let's say we compare, let's see here, HF versus an HCl bond. Like, what if we want to figure out which one is more polar, which bond is more polar? All right, so we just go to our table S, and we simply zoom in here on this thing, at least I am. 2.2 for the H, and F is 4.0. Ooh, that's a really good score in college, by the way, for your GPA. You should remember that, guys. So 4.0 for F, 2.2 for H. Now you just subtract them. 4.0 minus 2.2 is 1.8. That, I have to say, is pretty polar. That's a large pull. The H is not caring about electrons nearly as much as F is. So F is going to win that battle every time. In the case of H and Cl, let's see if it's more polar or not as polar as the other one. H is 2.2, Cl is 3.2. Now, oops, let me zoom in. There's the Cl 3.2. Well, now the difference is not as big. If you do the math here, you're going to see that it's only a difference of, let's see, 2.2 there, 3.2 there. Subtract the big minus small, you get 1.0. That clearly is not as polar. So the first one is more polar. And this one's less polar. That's what bond polarity is, okay, Skylar? So that's the first thing you want to know about polarity. The greater the difference, the more polar. The other thing, too, and this is for all of you here, please, please, please be careful with your subtracting. I had a student years ago missed 100% in the Regents because she subtracted these numbers, something like this, wrong. She did it in her head, but she didn't do it correctly. So please be careful with subtracting. I know it seems simple. Why would I need a calculator for 3.2 minus 2.2? You'd be surprised the mistakes people make, and so on. So please, you want to get that 100. At least I want to see everybody get 100. So now the other one is molecular polarity. Now this one has to do with shape. So there's an acronym I used earlier tonight, which was SNAP. And so if it's symmetrical in shape, it's nonpolar in shape. And if it's asymmetrical, it's polar. Okay, so, and the thing is, here's the problem with this. A lot of people try to draw these molecules, and they say to themselves, well, it looks symmetrical. Doesn't look symmetrical, so then they try to guess the polarity there. That can be tricky, though, because sometimes if you draw it one way or the other, you might actually think it's symmetrical when it isn't, and vice versa. So my suggestion is there's only about 3 or so examples on each side. I would just know the examples. I really would. So for the symmetrical side, the one example, it kind of fits into, it's really several in one, are the diatomic molecules. diatomics mean that in nature, these elements exist as two atoms put together. So when you're breathing in oxygen, which we are doing right now, or nitrogen, which we're also doing, those molecules are something two, O2 and N2 as well. And so that's what it might look like. The other ones that you should know, there's F2, there's Cl2, Br2, and I2. There's also hydrogen as well. Those are all symmetrical in shape, so you should know those. Those are all nonpolar. You can think of the nonpolar as being the electrons are distributed evenly throughout the molecule. So again, there's no real pulling to one side. So like if you drive your car and your car is staying pretty straight in the road, it's not pulling, that's kind of like nonpolar. But if it pulls to one side, that's more on the polar side. That's the other one. A couple more that are nonpolar, CO2 and CH4. Those are a couple more you should be aware of. Now, interesting thing about both of those, by the definition that we're using in this class, the actual bonds themselves in these are actually polar bonds, but because of the shape of them, the polarity cancels out. So the overall shape is actually nonpolar. So keep that in mind. The bond polarity is different, remember. And then the same thing with this one. Now, this is hard to draw the actual real 3D shape, but again, it's the H's are sticking out equal angles outside the carbon, so that, again, there's no overall polarity. So the diatomics, CO2 and CH4 are the good examples for symmetrical. As far as asymmetrical goes, there are three. Again, water is a good one. Now, of course, polar bears need water, but what about Santa Claus? He lives on the North Pole. Come on. He needs water too. So polar, North Pole, water, make that connection, please. HCl, also polar, and NH3. Those are the three big ones that you will likely run into. Okay, so hopefully that answers that stuff. Again, the big thing is if you know these examples, you should be able to get that kind of a question right for tomorrow. Sometimes they will say in terms of electron distribution, what makes it polar? You can just simply use the words symmetrical or asymmetrical, really, and you can get credit for that. So thank you again for that question. It sounds like we have our next one. Go ahead.
The next question is from Katrina from Sequoia, and it is the difference between ground state and excited state.
Ground state and excited state, yes. So I don't know, Katrina, thank you for the question. If you eat hamburger, but hamburger is actually in the ground state. I'm just kidding. That is true, but not for the purposes of the test here. And did you know that coffee, right? The reason why coffee tastes like dirt is it was ground that morning. I'm just kidding, but anyway, no, ground state refers to the lowest energy positions. So lowest energy positions for for the electrons. Okay, so what you look for is on the periodic table, those electron configurations. The way they're written out, this is the ground state configuration. So if you look at, say, chromium right here, Cr, it says 2, 8, 13, 1. That would be the ground state for chromium. That means that there's 2 electrons in the first energy level, 8 in the second, 13 in the third, and then 1 in the fourth. That's in their normal lowest energy positions. Now, if you, Katrina, or anybody else who's watching this likes to follow sports like I do, you know that when you're watching a sport, a lot of times if your team is winning, or maybe if you're watching baseball or something, your team scores a run, you get all excited, right? So you kind of move, you kind of jump out of your seat, you start saying something. I don't know if these two gentlemen here, I'm sure they go through stuff like that. Maybe not the same sports I like, but others. Of course, I know that football and soccer and other types of sports they like, baseball, things like that. But the excited state is a temporary position where electrons gain energy. So in the excited state, one or more electrons is at a higher energy state. So in the case of the chromium, what would happen is you would change what it is originally. You would maybe make it 2, 8, and then maybe move one of those 13 electrons into the fourth energy level. So you'd be left with 12, and then this would be 2. So 2, 8, 12, 2 instead of 2, 8. Oops, I got to move that up so you can see it. That would be an excited state. But the thing is, here's the thing. So you're excited about watching this game. Your team's winning, but then 2 minutes later, your team's losing again. Now you lose all that excitement, and you go back to where it was. So the excited state, again, is a temporary position. The electrons will not stay there. So when they then move back from the excited to the ground state, usually they give off light. And that's where you get those pattern questions where you have all those lines and you have to match up the spectral lines with multiple elements, things like that. So, but that's really the difference between excited and ground. The ground state is on the periodic table. The excited state is not. And by the way, there's more than one way of doing the excited. You could do 2, 8, 11, 3. There's a lot of different ways you could do it. So it's not just one size fits all. Thank you again for that question. Next person here.
So Rams are trash, aka Matty B Ice.
Okay, yeah, Rams are trash. Yeah, okay.
Ask the different types of what the different types of chemical formulas are. So like empirical versus
empirical.
molecular.
Yep. Well, I can guess who this is. Thank you, Matt, for the question. He's a Seahawks fan, so of course he's going to say that. Anyway, what do we have here? We have so empirical versus molecular. Is that what he asked? Just those two? Okay. Empirical versus molecular. Let's start off with the easier of the two, which is molecular. So in many ways, because molecular is the actual formula. Like if you were to analyze a compound and figure out what is the actual formula, that's the molecular formula. Now, of course, when we're talking about molecular formula, we're really talking about covalent bonding, so it really would be nonmetals and all that. So, for example, obviously, glucose, most people know from biology, is C6H12O6. That's a molecular formula. Sucrose is C12H22O11. Those are a couple of actual formulas. So that's sucrose right here. That's the stuff you put in white sugar, table sugar that you use in your kitchen. But there's a whole bunch of different ones. C4H10, that could be butane. Those are all molecular formulas. Now, the empirical formula, though, is the reduced formula where you reduce it down by way of dividing the subscripts by the greatest common factor. So this is like the simplest ratio of atoms. So if we take the C6H12O6 and we divide each of those numbers by 6, then I'm going to get CH2O. So C1H2O1 really is what it is. 1 to 1. It's the same ratio, but that's the empirical formula, which in many cases isn't even a real thing. The empirical formula may not exist in reality. In the case of sucrose, that cannot be reduced any further because 12 and 11 are stuck. There's no way to reduce a 12 and 11 at the same time. So that's got to stay as that. So sometimes the empirical and the molecular are exactly the same. In the case of the third one, you could divide these numbers by 2, so you would get C2H5. So different ways of doing it, or different examples, I should say, of how to do it. But again, the empirical formula may not be an actual formula in real life. It's just a reduced or a simplified ratio. So hopefully that answers your question. How did this student go by? Matty Ice, was it? Or?
Their name on Twitter is Rams are trash. And
the name? Oh, okay, all right. Yeah. Well, it must be some other. It must be the animal they're talking about.
And their username is Matty B Ice.
I got you. Yeah. Okay. You had another question, right?
Yeah.
Go ahead.
All right, this question is from Mackenzie from Sequoit, and they asked the different reaction types such as decomposition, synthesis, and single replacement.
Yep. So thank you for your question. The main 4 types that you probably learned earlier in the year, there's synthesis. Synthesis is actually, you've heard of photosynthesis, of course, and that's essentially you're making something. So you're going from small to large. A lot of times it looks like nuclear fusion, but you'd want to use the word synthesis if you're not talking about a nuclear reaction. So we actually did one of these earlier. We balanced the hydrogen plus oxygen to give you water. That's synthesis right there. You actually are adding those two together to make water. You're making a larger product, in this case the H2O. Whereas decomposition, you're decomposing it, which means you're breaking it apart. So you could take, for example, sodium chloride, and if you break that down into 2 sodiums and then chlorine gas, that would be decomposition. Now understand that these reactions may not necessarily occur in everyday life. We would certainly hope that NaCl, as you're sprinkling it on your food, let's say, doesn't spontaneously decompose into sodium metal And chlorine gas, I think we'd have a problem if that happened. But decomposition, again, you are breaking something down from large to small. It could be in both these cases. They don't have to be elements combining or as ending up as products. They could be smaller compounds too. Like even photosynthesis is a little bit more complicated than this, but you get the idea. Single versus double replacement, those are always tricky. Single replacement is where you have an element and a compound on each side. And so if you had something like zinc plus HCl gives me zinc chloride plus H2, you notice here that there's an element Zn, but then on the other side it's part of a compound ZnCl2. And then over here you have HCl, which on the other side becomes H2. So you have an element on each side that then combines with, or has a compound next to it as well. Now, keep in mind, this is a good thing for everybody. Sometimes they will draw single replacement as what I like to call disguised single replacement, where they might leave out part of the compound. So they might write this out as Zn plus 2H plus gives me zinc 2 plus H2. This is really a single replacement as well. What they did is they just left out the negative ion that goes along with the H plus or the Zn2 plus. They just left it out because the Cl isn't doing anything. It's just sitting there. So a lot of times you'll see the single replacement kind of hidden. And the nice thing about, so the thing about the single replacement reactions are always redox reactions because you're actually changing the oxidation states of two elements. In particular, the zinc goes from a charge of 0 or oxidation state of 0 up to a +2. And then the H goes from a +1 or plus to a 0 here. And you can see the same thing here. So single replacement are always redox reactions. If you get a question like that, which of the following is a redox reaction, and you see already it's single replacement, you could automatically pick that. But on the other hand, the double replacement, which, there's a lot of different ways you can do, examples of these. These are never redox reactions. All you're doing here, and they actually had a question about this a few years ago, all you're doing is you're exchanging ions. So when you exchange ions, you're not actually changing the charges at all. You're just you're rearranging them. And so, if you had like Ag NO3 plus, KCl or something, and then you end up with AgCl plus KNO3, all you're really doing is you're switching the silver and the potassium. They do get more complicated than this sometimes if you have to deal with balancing them. But the basic premise is you have compounds only on each side, so two compounds. Occasionally you'll see one where one of the compounds that's a product can actually split into two, but normally you'll see two on each side. And all it is just exchange of ions, and these will be done in solution, in water, aqueous solution. One example of this too, another example is neutralization, which is really a type of double replacement with an acid and a base where you have something like HCl plus KOH gives you KCl plus, and you're always going to get water as a product, but what I usually tell students is to write it out as HOH because then they can see it better. The H combines with the OH to make water, or HOH, and then K and Cl go together. You should be putting the metal first, but the Regents answer keys sometimes are more lenient than they could be. But yeah, hopefully that answers your question. Those are the four main types of reactions you probably did earlier in the fall, I'm guessing. Go ahead, Carson. You got another one?
All right. So, if I can get the microphone. We Are the Harrys said, hi, it's me again. I was wondering if you could go over some of the math involved, like heat of fusion problems. Thank you. You're a great teacher.
Well, thank you very much. I appreciate the comment, and thank you for the question, too. I'm always appreciative of these questions because it means that you care about your grade, and you're trying, and you're interested, and all that stuff. So I heard heat of fusion. Now, not to confuse this with the fusion I did earlier. The fusion I did earlier was a nuclear process, whereas heat of fusion is far from that. So there are three heat formulas that you may run into tomorrow, and they're right here. They all start with the letter Q, because as we all know, the word heat starts with Q, so naturally that makes sense. But all three of them involve the symbol M for mass. So heat is not exactly interchangeable with thermal energy, but you can kind of relate them together very well. So I've been seeing a lot more questions recently about, compare the thermal energy of a 5-gram sample to a 10-gram sample. And so, because mass is part of these heat formulas, the more mass you have, the more heat involved, so to speak. So that's a question I've been seeing in the more recent exams. But nonetheless, all three of these examples involve multiplying mass by something. Now, the first formula involves multiplying the mass by what's called the specific heat capacity of a substance. That's a constant for the substance. So essentially, it's how much heat it takes to raise the temperature of 1 gram of something by 1 degree C or 1 Kelvin, which is actually the same increment. And so for water, you can find the actual value of it on the front page, 4.18 table B, joules per gram Kelvin. But again, you could use Celsius, joules per gram degree Celsius too. It doesn't matter. You don't need to convert. In fact, definitely don't want to convert between units because the increment size is the same. So therefore, you could use C or K for that particular unit. It's just a constant, and the units for constants are based on the other numbers in the problem. So C is 4.18 for water, and then delta T is simply change in temperature. So if you had a problem with this, what you would do is multiply the mass of, say, water times the specific heat. And then the problem would have to tell you something about changing the temperature. And so where would that happen? If we were looking at, say, a heating curve, for example, you would have something like this, let's say. You have solid, liquid, gas. And because the temperature, let me zoom out so you can actually see this now. The temperature where it changes is where you would actually use the MC delta T, and that's along those diagonal lines. So along this line, and this line, you can use Q equals MC delta T because the temperature is changing. In other words, the kinetic energy is rising along those diagonal lines. And so whenever the temperature changes, you can use MC delta T any of those 3 spots. So they would give you the 2 different temperatures, or you might have to look at the graph and tell, what's the difference in the temperature. Now, one thing they have been asking a lot over the years is instead of solving for Q, you might have to solve for either something like C or M or even the final temperature. Every single time I've ever seen a final temperature question where it says, what is the final temperature after adding or absorbing heat? Every single time I've ever seen it, it's always absorbing heat, so therefore you add to the original temperature how much the temperature changed. So what you would do is in most cases, you would solve for the delta T and then just add that number to the original temperature. That's usually what I've seen. It doesn't mean this year they can't do the opposite where we say, okay, let's say we release some energy, in which case you would have to actually subtract that delta T from the original. But hopefully it doesn't happen. We haven't seen it before that I know of, and so on. But the delta T is, that's useful, that formula, the MC delta T, if you have a change in temperature. Now, as far as the other 2 are concerned, and your question had to do with heat of fusion, this, the key with this is knowing what heat of fusion is. Heat of fusion, so fusion is melting. So the heat of fusion is how much heat's needed to melt 1 gram of something. So in the case of water, I can actually find the heat of fusion of water. There's the symbol HF. I can find it right here on the front page. 334 joules per gram. So that's how much heat you would need to add to a gram of ice to melt it, and so on. So 334 joules per gram. And along this curve here, heating curve, you would actually use that equation right in this first part because this right here, solid to liquid, that's melting, right? So melting is solid to liquid. Keep in mind, though, you can use the equation from liquid to solid as well. It's heating curves and cooling curves, which are the opposite, are reverse processes. So if you absorb energy one way, you release energy the other. You can still use the same equation. But that formula is actually a lot easier than the first one because it's just 2 numbers multiplied. And then the last equation here is MHV, which is mass times heat of vaporization, which is the other constant here, heat of vaporization, let's say for water. Notice how much bigger it is, 2,260 joules per gram. But that makes sense because water is the molecules have to be separated, and you have those hydrogen bonds that attract them together. You have to break those apart completely, not partially, so it takes a lot more heat to do that. That's why you need to raise temperature of water to such a high temperature just to boil it, and so on. But that would be along this part of the graph right here, Q equals mHV. Notice also that the length of the line for the vaporization is longer than it is for the fusion or melting. Again, because it will take more time to essentially break apart those attractive forces. So definitely more heat's required to do that. So I hope that answers your question. Thank you again for asking that. What we got next? So nothing at the moment. So I know we're obviously past 8 o'clock, but I did have a couple more things I wanted to share. So a couple of things that students often mix up, well, actually one, is when the pH rises, don't forget that the hydronium or even the H plus concentration will decrease. So as one goes up, the other drops. Now remember that when pH rises by, say, 1 unit, pH goes from, say, 1 to 2, the hydronium or the H plus, either one, that goes down by a factor of 10. Okay, so there's a question. So just keep that in mind. So when you raise the pH by 1 unit, you drop the H plus or H3O plus by 10. It's logarithmic, that's why. If you raise the pH by 2 units, you would drop the H plus by 100. So, okay, it sounds like we have another question. Go ahead and, Stevie.
This is Katrina from Sequoia, and they asked, could you go over the redox reactions?
Redox reactions, I assume, so it's kind of general question, like what they look like. So redox, which is always a tough topic, so I'm glad one of you called in on this because it's really not easy at all for a lot of students. Understand that redox is the combination of reduction and oxidation. So I usually like to do oxidation first. Oxidation is simply loss of electrons. And when you do oxidation, understand that you're losing a negative. So when you are writing out one of these half reactions, understand that the charge or the oxidation state is going to actually go up as a result because you're losing a negative, right? You lose a negative in math. If you subtract a negative number, you actually get a larger value. So if I start out with, say, zinc with a charge of 0, that's pure zinc, and I got rid of 2 electrons, I would be left with Zn with a charge of either plus 2 or 2 plus, depending on how you see it. They actually can be interchanged. Sure, there is a difference technically, but I mean, for a single element like this, it's not any different really. It comes into play more with larger ions. But anyway, 0 to 2 plus, that's a difference of 2. So I would have 2 electrons on the product side. That's the key. The electrons have to be here, okay, when you do oxidation. And you always do it as plus E minus. Always do it like that. Okay, that's the safest bet. That's the only way you're ever going to see it on a Regents question. They're going to do something plus E minus. And also don't forget the negative sign. The negative sign is just as important as the other stuff. So be careful with that. And so oxidation, you're losing electrons, and the oxidation number will actually increase from start to finish. Whereas reduction, that's gain of electrons. And so the half reaction for reduction, you would actually have the electrons on the left side. So for example, you could have Cu2 plus 2 electrons gives you Cu. And notice this time, the charge goes from a positive 2 to a 0. It's actually dropping because you're reducing it. You're reducing the charge. That's what reduction means. So by reducing it, the charge drops. Therefore, you're left with that. Now, your question mentioned redox reactions, so I assume that this is not necessarily all that you were looking for. So we started to look at a minute ago with if a reaction is redox or not. The thing is, a redox reaction has to have the combination of the oxidation and the reduction. So to be a redox reaction, you have to somehow find 2 processes occurring, one oxidation, one reduction. And a lot of times they're easy to recognize. Like if I took those half reactions and shoved them together, I would get this. right? But you can tell that that's redox because the zinc being alone on this side is a charge of 0, and the copper is a charge of 0 there. Because there's those elements changing their charge, automatically that's a redox reaction. You can right away tell. But if you don't have something as simple as that, you might have to analyze it a little bit further. And we saw like something like the zinc plus the the HCl that I did earlier. You may find that you have to actually go through and check every element. A little bit harder, not terribly hard, but here the zinc is 0, here the hydrogen 0. But you'd have to go and check to see, okay, what are the individual oxidation states for the H and the Cl. And the H here, you look at your periodic table, and you'll see that it is, you go with the topmost choice if you're not sure, +1, which is far more common than -1 for hydrogen. And then you have to understand and remember that the sum of the oxidation states for a compound, if I zoom out again, has to be 0. So if the H is +1, the Cl must be -1. On the other side, the zinc chloride there, we look up the zinc, and the zinc is +2. And so now we have to put that in, and we can see that that'll balance out a -2, but because there are already 2 chlorines, we would need to put each one as being -1. So the thing is, you may have to do some of that kind of stuff potentially, but you can see right away that clearly there's 2 elements that are changing their oxidation state. So those are redox reaction types. Balancing them can be tricky sometimes, but like I said earlier, when you balance equations, usually they're going to put small numbers like these. I mean, technically you're actually balancing a redox reaction when you do a single replacement like this. But I mean, there could be one where it's like aluminum plus, Cu2 plus gives you Al3 plus Cu, like this. And this technically is a redox reaction that you theoretically could have to balance. And probably the easiest way to do it, well, I shouldn't say easy because everybody has different ways of looking at it, is notice that all of them are 1s in front, so technically everything's balanced from the atomic atom or atomic part, but the charges are uneven. So whatever coefficient you put in front of the Cu2 plus and the Al3 plus, that will multiply by that charge. So if I put a number in front of Cu2 plus, then the overall charge is 2 plus times that number. Likewise, 3 plus times that number. So to get 2 and 3 balanced, that would make 6 on each side. So that would make, I need to put a 3 there to make +6, and then I need to put 2 there to make +6. But now I've screwed up the aluminum and the copper, so I got to put a 2 there and put a 3 there. So, that kind of thing you may run into as well. But those are some examples of redox type reactions. So hopefully that answers your question there. Carson?
All right. So 2015 Royals 4L1 asked, can you draw an isomer of an organic compound?
Well, I'm guaranteeing that the person who sent this in is not actually a Royals fan because there's probably only 3 in the world. I was kidding, but I'm sure there aren't too many around here. Draw just an isomer. Yeah. So I had this one earlier. So if you already have a molecule, like this one, they've asked this one before. Like, okay, draw an isomer of this, something like that. So they'll have all the H's sticking out. These are all H's here. One thing you can't do, and this is a mistake a lot of students make, they'll just redraw the same picture just upside down or something. Like they'll just draw it like this, where you have the carbon sticking up instead of down. You can't do that. You actually have to make it such that the name would be different and everything. So the best way to do this one, actually the only way really, would be to take all 4 carbons and stick them in one chain, like that. See what I mean? And so if you do that, then all the H's would just simply go out on the outside, and you'll find that those H's are the same number, because remember, isomers have to have the same molecular formula. So if I take each of those separately, the first one is C4, and there should be 10 H's altogether, as is the second one. So they're both C4H10, but they're actually drawn differently. So that again is the way it works. Now, there's a lot of ways you can draw isomers. I mean, they don't have to be hydrocarbons. You could draw table R. There's a lot of compounds here you can draw isomers of. like if you want to draw an isomer of an alcohol, you could actually make an ether. So, did you just get another question?
No, I was just
Okay.
There's something related to this, and I was
Oh, okay. Let me just do one, just another thing here. So, like with an alcohol, for example, the OH, you might have the OH like that. But if you could actually make an ether using the same atoms, I'll just leave those as dashes for now. But you could actually put the C's, separate them, and put that O in the middle, like this, and then put these as your 6 H's. So, I mean, you can make isomers that are not even the same kind of compound. Like an alcohol and an ether could actually be isomers of each other as well. You could actually have isomers, aldehydes and ketones. I mean, they can be isomers as well. Organic acids and esters can be isomers of each other. So it really just depends on how you draw it. As long as you don't violate any of the rules on bonding, carbon has to have 4 dashes around it, 4 bonds. H should have 1. O will have 2. N will have 3. At least, in all these molecules we're drawing, you're good. I mean, really, as long as it doesn't violate it. So, good. Well, thank you for the question. Go ahead, Carson.
All right, so kind of related to that, Caitlin Mazzata asked, can you go over a 2,2-dimethylpropane structural formula?
So, 2,2-dimethylpropane.
Yep.
Right. So, and thank you for the question, Kayla, the thing about this is you start off with the ending, really. You go backwards. So ANE ending refers to the fact that it is a hydrocarbon that fits under the alkanes. See the alkanes here? Alkanes always have single bonds. So there's no double or triple bonds anywhere in an alkane, or up here actually. And so then from there, you simply look at the word before it, or the prefix before that, that says prop. So if it's propane, then all you have to do is simply find prop on table P, and that's 3 carbons. So your starting point is going to be 3 carbons like this. And then that's like your base chain is 3 carbons. And then earlier it says dimethyl. So meth as a prefix means 1. So 1 carbon. But because there's 2 separate methyl groups, it says dimethyl. Di just means there's 2 of them. So the question is, where do you put them? Well, technically there's only one place to put them, but they do tell you here with the 2,2, that tells you that they're on the 2nd carbon from, in this case, either side. So if you call this the first, that's the 2nd, that's the 3rd, then you would just put those 2 methyl groups, one up, one down, and then the rest of it's just drawing in your H's. So these will all be H's sticking out here, if you want to put the H's in. But that's how you would draw it. The numbers in front are the location of the extra groups. The die just tells you how many you have. Now, most likely you'd have to draw something like this more than name it. But naming could be something you do in the multiple choice too. So they could do something like that. Yeah. Yep, well, thank you for the question. Sounds like we got a phone call here. Go ahead.
We have from We Are the Harrys on Twitter again. How do you know which charge to use? Roman numerals, question mark.
Oh, Roman numeral one? Yeah, so, okay, so when you're talking about naming stuff, if they, say for example, let's say they give you the name of something, like copper 2 chloride. When the Roman numeral is already given, that means you know automatically what oxidation state or charge to use. The symbol for copper is Cu. This Roman numeral 2 is +2. That's what that means. So that Roman numeral matches the charge that you have there. And then the chloride, you look for, well, you really need a negative to balance out the positive there. And chlorine, the only one that's possible is the -1. And so there you go for that one. But you would put that there, then you would just crisscross them, and then you would get CuCl2. That's if you have the Roman numeral already there. Now, what if the Roman numeral isn't actually there? Let's say they gave you the formula and you didn't, you had to figure out which one to use. In this case, let's say you had something like Fe, Cl3 or something. So in this case, you look at the actual formula, and we know that chlorine is we saw the -1, so that most likely works there. And we need the sum of those oxidation states, or those charges, to be 0 for a compound. -1 times 3 is -3. This has to be +3. So now we see that it's a +3, and we also notice that iron can be either +2 or +3. Because of that, we do need to use a Roman numeral in the name. So as a result of that, we would have to name it as iron 3 chloride. So the Roman numeral, what I would suspect is if you have a Roman numeral question, they'll give you the name first and not the formula. But you might have to draw the name or draw the formula from the name or write the formula out. One year, about 10 years ago, they did a really tricky one where they used the element vanadium. And vanadium has the symbol V, but when they wrote it out, they used Roman numeral 5. So they actually did vanadium V, and then I forgot what the ending was here. But students got confused because they thought the V meant the symbol for vanadium. So it was kind of a tricky thing to do, but the Roman numeral, the thing in parentheses will always be a Roman numeral, not the symbol of the element. So just keep that in mind. And so you do want to know your Roman numerals. Understand that it's I would say 1 through 6 would be the 6 that you'd want to know for Roman numerals. Let me just quickly do that. I know there's a couple other questions here. Roman numeral 1, of course, is just an I. 2 would be like this. 3, 4, 5. You might just see a V. You might not see the horizontal lines. And same thing with 6. So they could do it like that, or they could put the horizontal lines. So you should know those just in case. Those 6 Roman numerals, I'd say, would be helpful to be aware of. But again, hopefully that answers your question. Again, you shouldn't really have to guess what oxidation state to use. If the Roman numeral is given, that tells you which number to use. It has to match exactly. And it only works for the plus charges. The Roman numeral, you don't use it for negatives. In the case of negatives, typically you use the very top one. Like the chloride, I use the -1, that kind of thing. So, okay, what's next here?
Caitlin Mazzata asked if you can go over acids and bases.
Acids and bases, yeah. The big thing about acids and bases is there are 2 reference tables, Kayla, and thank you for the question. Acids have, generally in their formula, they have H at the beginning. So you'll see that all these acids here have H. Just about all of them have H at the beginning. So when they're in water, as long as they're in water, they will produce H plus ions. So like HCl, you put it in water, it'll actually produce H plus and Cl minus. Now keep in mind that when you put it in water, actually you could write it out a little bit differently, where the HCl is actually donating an H plus to the water, and so you'll get H3O plus. This right here is called hydronium, and that's really the ion that is found in acid solutions that we would find present in the water. But acids, yeah, all acids for the most part will start with hydrogen in their formula, and when they're mixed with water, they will produce H plus or H3O plus. That's the general definition of an acid. But again, use your table because a lot of these are right on here. Because acids break up into ions like this when they're in water, they are types of electrolytes. So you've seen that word a lot, I'm sure. Electrolytes are substances that when you put them in water, they conduct electricity because you have these ions that are mobile. Mobile ions, they are able to move around and allow electricity to pass through. That's what it's all about. I know it's a cool word to say electrolyte, but I guarantee that people that see it all the time on Gatorade bottles don't necessarily know what it is. So now that you've seen that, electrolytes, again, you can remind people what that means when they're buying Gatorade or whatever brand at the store. They know it actually is a chemistry thing. The other thing, bases here, on the other hand, usually produce OH minus when they're in water. If you look at table L, so like for example, NaOH will produce Na plus and OH minus. And this right here is called hydroxide. That's the ion that is produced for bases in water. Bases are also electrolytes because these are again mobile ions. So bases can conduct as well when you put them in water. Again, when they're not in water though, you wouldn't expect them to conduct because of the type of bonding this has with the ionic bonding between the Na and the OH part. You would not expect it to conduct. But that's essentially the main definition of acids and bases. There is another definition that says acids donate H plus and bases accept it. This is the more traditional definition. The other one's called the alternate theory. And if you think back to those acronyms that I mentioned earlier tonight, a good one for the alternate theory, if I have them, I know I have them here. Here they are. A good one for the acronyms is the BAD idea. Bases accept, acids donate. And that's the second definition, the accept and donate. They do ask that question quite a bit, though. Like, water acts as a base when it A, donates H plus, B, accepts, so that kind of thing. So they will ask that as well. But usually it's more to do with this kind of stuff. Well, thank you again for that question. Hope it answers what you're looking for. Next one, go ahead, Sevi.
This question is from We Are the Harrys on Twitter. And they ask, can you show how to name compounds with the reference table with the prefixes?
I mean like probably the di and tri stuff. So I'm going to be honest with you. They're not really going to make you do that. I don't want to not answer your question. But from a priority standpoint, as far as the Regents is concerned, they're not going to ask you to do like carbon dioxide. They don't typically, if I ever have done that. But really all it is, if you did have to name it, you really wouldn't use the periodic table. With the prefixes, you would just do, unless you're talking about a different prefix, unless you're talking about the organic stuff. But I think you're talking about like the prefixes di and tri and all that. I mean, like you all probably know that CO2 is carbon dioxide. That you wouldn't even need the reference table for. You just use the prefix di for 2. But that's not something that I would really worry about. The only prefixes may be these. And if you're talking about this, you would have to have either the substance drawn like structurally, or it could be a situation where you have the general formula. I could just do a quick one here. If you had something like, C2H2 or something like that, and then you would say, okay, well, there's, you might want to draw it first. Actually, it turns out to be this one, and you would use the prefix for 2 carbons as eth, so it's actually eth, but with the triple bond it'd be ethyne. So I mean, if that's the prefix you're referring to, that's where it would tie in. You just count the number of carbons for the organic. But like I said, the other prefixes, di and tri and all that stuff, I wouldn't worry about it from the standpoint of any other kind of compound. I know most teachers go over that, but it's really not something I would worry about naming. Usually it's the Roman numeral stuff, usually ionic, like some metal and non-metal, or metal and a polyatomic ion, something like that. Yeah. So, but hopefully that answers, at least explains why I didn't go over in more detail what I think you were asking. Sorry. Go ahead, Carson.
So I actually didn't catch this person's name. I didn't hear it on the phone.
That's all right.
But they are from Sequoia, and they asked about Lewis structures. They might have not been here when you went over it.
Yeah, Lewis structures, the trick with these is you have to, and I'm really going to focus in on the covalent ones because those are the ones that typically will be asked. You essentially add up all the valence electrons from the elements that are involved, and then you just try to piece them out so that each atom ends up with 8 electrons around it, other than hydrogen, which only will have 2. So I did one earlier. Let's try a different one. Let's try even something simple like Cl2. I mean, this is something that they could certainly ask you to draw. So you go on here, you find your valence electrons. Let me zoom in on that. 7 valence electrons. But because there's 2 atoms, 2 times 7 is 14. So I want to multiply that by 7. 2 times 7 is 14. 14 electrons, great. Now the trick is, okay, how do I piece them, put them in the right place to get the right structure? The CLs are next to each other. What you usually want to start off with is 2 dots between them, or 1 dash, depending on how you prefer to do it. I actually like the dashes better, but either way is fine. And then just place the dots around it so that you get 8 around each one. And then at the end, make sure you add up to 14. Okay, right now I have 8 around each atom, if you think about it. 2, 4, 6, 8, 2, 4, 6, 8. I'm sharing the 2 in the middle. That's my covalent bond. 2, 4, 6, 8, 10, 12, 14. That's good. Or I could do it with the dots like this. Okay, so again, the big thing is, at least the way I do it is I just add up all the electrons together, just the valence now. Now, some people use dots, some people use X's, combination. It's up to you. I mean, I just don't do it that way. It doesn't mean it's wrong. You're a different way, but this is how I see it. So go ahead, Stevie.
This question is from Woody, and they asked if you could go over adding temperature and concentration and subtracting temperature and concentration in equilibrium.
For Le Chatelier's, yeah. So Le Chatelier's principle is where you kind of mess up equilibrium a certain amount. So if we were to write out a fake equation here, put in my double arrow there. Yeah, so the trick is with the temperature ones, and thank you for the question. The trick is with this to figure out if you're raising the temperature, you're really raising the energy or the heat. Sometimes it'll just say heat instead. Or it might even say kilojoules or something, some sort of heat term. If you raise that number, then you got to shift the opposite way to get rid of the extra heat. In this case, you'll actually shift in this direction. When you do shift to the left, what's going to actually happen is the amounts of anything on the left side of the equation will actually rise. This will go up, this will go up, and this will go up. And anything on the right side will drop in concentration. But then the energy will actually drop too, a certain amount. It'll go up, and then it will start dropping to a lesser level than it was at its peak, but it will still be higher than it was initially. So think of it this way. You have too much energy in the right. You got to shift the other way to get rid of the extra heat. That's if you raise the temperature. Now, if you lower the temperature, if I use the same equation here, if I lower the temperature, then I have to replace or replenish the energy that I got rid of. So then I would shift this way, causing this to go up. Ultimately, the temperature will go up a little bit from where it was there, but these will all drop. So getting rid of something, the idea is you have to restore it by shifting toward that side. And really, to be honest with you, when it comes to temperature and all that, you can treat this as if it's concentration. No different than if you were to raise the amount of A. If you raise the amount of A, you just shift to the right because I'm trying to get rid of the extra A. If I raise the amount of G, on the other hand, I would shift to the left to get rid of the extra G. So I think either way, you're perfectly fine with thinking of the heat like that. So, yep. Very good. Thank you again. Hopefully that answers your question. So I think, we've had a good 2-hour session tonight, which is pretty cool. I'm glad to see so many questions, and I really appreciate all of you staying as long as you did. And I think tonight is just one small piece for tomorrow. Certainly tomorrow morning at your school, perhaps your teachers will do review classes. Perhaps you can get some time in to study before. I wouldn't study too late. I wouldn't study up until 11:59 in the morning. But give yourself a break, maybe up to 11 at the latest. Do some studying if you need to. But good luck to all of you. For some of you, this may be only your first or second Regents ever. It's not the easiest test in the world, but at the same time, if you've done practice tests, you'll see a lot of similarities with other tests. And so hopefully everybody does really well on it. And again, I'm Mr. Costanza at Whitesboro, and thanks again for tuning in tonight, and thank you to Carson and Stevie for handling the phone calls and tweets so nicely for us, and thank you to Joe in the back. It was a pleasure working with all of you tonight. Have a good night, everybody.